So hi everybody. This presentation is about communication, so the underlying level of how nodes communicate to each other. It's really hard to talk about communications right now because communication as a module is undergoing a heavy reconstruction process. So I reckon I will just divide this presentation into two slots, separate slots, where in one I will tell you right now how communications runs at the moment. And there I will try to show where the problems of that are, and then I will switch to what we are actually going to do in the next upcoming releases. And also I'll be covering some topics of how you will be able to interact with the node to get some information from communications layer. So whenever you connect to your node, you provide an address which has a key, which should be a public key, and that key identifies your node globally around the network. It has a host and UDP port. Well, that's ideal situation, but that's a lie, because right now within the code it looks more like this. Even though we have public keys, when we use public keys, that name is just randomly generated. And this is one of the things that we have to be really quickly refactoring, but just saying this is how it is. So even right now, if you instantiate your node, you can provide this value as a parameter, which at the end will not be the case. You will have your public key, and that public key will identify your node globally among the cluster. So node discovery within the network happens through a peer-to-peer protocol, which is called Kademlia. I will not go through that protocol because I don't think it's really not that necessary. If you guys are interested of how it works, the paper that underlies the algorithm is pretty short. It's like 13 pages. It's quite easy to read. Essentially, they have a very cool algorithm to identify the nodes among the network. The algorithm converges to the node that you're trying to find very quickly. It has good performance, and also has a huge robustness and reliability against DDoS attacks on the network. From the paper, we actually so there are some protocol messages which are being sent through Kademlia protocol. We are covering only the ping and find node and store, not find value, because those are the actually that we really need at the moment. Yeah, this is probably too small, right? Yeah, I thought so. Unfortunately, I'm prepared. So the way that we so let me look it up. There we go. Is it good enough? All right. So the way that we implemented the protocol is using protobufs. So those are the messages which correlates directly to Kademlia protocol. As you can see, the protocol message can be one of the ping or ping response, lookup message and lookup response, and disconnect, or something which is called upstream. And upstream was a design decision that I think I would like to remove from the protocol, because the idea was that the protocol message can be one of the elements from the Kademlia algorithm or some other message, and of any type. As you can imagine, this sort of breaks the niceness of having the language, which is like Scala, which is statically typed, because at this point I have to sort of deal with messages that can be of any type, and then I deal with strings, and it feels like programming with some dynamic language. So this is something that I would like to remove, but this is also something how the protocol works right now. So we have this message protocol, and it can be just basically one of those things, or some other message that we were sending. So in a moment you will see like messages like encryption message and encryption message response. All of them will be hidden here under this upstream field. I have to jump between my slides and my code. But yeah, so this is how right now nodes connect. Imagine that you have some node with some address and some identifier, and you try to connect to it because maybe this is your bootstrap node, or maybe you learn about this node through the node discovery algorithm. Regardless of how you learn about the name, at some point you will try to connect to it. So what you do is you send a message, which is called an encryption handshake. And that message holds internally your public key. So this node's public key. That message is being sent to that other node. Nice animation, right? My own work, thank you. So this node right now will learn your public key and will send you an encryption handshake message response back with its own public key. So at this point, both of the nodes exchange messages, and they learn each other public key, right? So then the second phase of the protocol is sending something which we call a protocol handshake. At the moment, protocol handshake doesn't care any information whatsoever. However, what important is right now is that this message is framed, and that frame encrypts that message. So it's already encrypted using the previously exchanged public keys. So that message goes to that node. If that node is able to decrypt the message, he sends the response back. And once that exchange happens, both nodes consider themselves as if they are connected to each other, and then can now exchange other messages and communicate. So there is also some optimization within the algorithm. So you can imagine that if two nodes were connected between each other in the past, one of the nodes, I don't know, dies or whatever, then comes back, and he tries to connect to the node that he's seen previously in the past, there's no point of exchanging public keys at the moment because that information was already exchanged, so he can directly go to the second phase of the protocol. If it fails for whatever reason, because under that IP address might be lying some other node with some other ID, he will roll back to the full handshake protocol. However, if that original node is still there, they will just send those two messages like protocol handshake and protocol handshake response, and that will be it. So one more time code. So proto. So not that proto, sorry. Here. So as you can see, this is one more time. This is how we deal with that. In one more time, this is a structure with protobufs. So our protocol message here can be either encryption handshake, or encryption handshake response, or it's a frame where frame at the moment can hold two messages, protocol handshake and protocol handshake response. And one more time, there is this upstream field, but it shouldn't really be here, and it will be definitely deleted. But that, just so you know, this protocol message is different from what we see a moment ago, because that protocol message here was from the underlying Cademia protocol, and we piggy write on that message, so that upstream here becomes one of the messages from our protocol when the nodes connect. And it seems weird, it seems complex, and it is, and it will be changed. So I showed you this, I showed you that. I can actually show you, if you guys are interested, like how many of you guys are actually interested how that is implemented in general terms? All right, there are a few people, awesome. So communication is provided as a detail. So the communication is provided as a type class, so that the type class is basically sort of an abstraction that we try to carry away from the underlying stuff that's going on within our business logic. So if I have Cademia's algorithm that needs to know how to send messages between other nodes, Cademia shouldn't really care how those messages are being sent as long as they are actually being delivered. That's why we provide this API. So for example, round trip method is just a function that you give him a message, you tell him to which node you would try to connect, you give a timeout, and then you send that message. And as a return, you get two things. You either get an error or you get a protocol message back. I don't know, the broadcast method is just broadcasting this particular message to every node that you are aware of. Find more peers is a function that will give you a list of nodes that you haven't connected yet. So the nodes that have been discovered, but you haven't seen them yet, and so on and so forth. And this is just an abstraction as a close over like type class, and in a moment you guys will see how that abstraction is being used. So you've seen a moment ago my little animation of how communication works. So this is exactly the same thing, but in terms from the code perspective. So we fetch a timestamp, we log something, we add some information to metric system, and we fetch the public. So we try to connect to this peer here, this little guy here, and we fetch the information, whether we have an information about his public key. We might have it, we might not. if we have if we don't have the public key for that particular node that we try to connect to, then we will have to go for the full handshake message. If we do have that message, then we will try to just go with the second phase of the protocol, and if we fail, then we will roll back to the full handshake protocol. And when that is done, we fetch another timestamp, we record something to metrics, and we're done. So now you might be asking, okay, so how full handshake this little guy is implemented? Well, full handshake is just run the first phase after the second phase, and the one that rolls back. So this little guy over here, you can see that it's running just the second phase. It writes the attempt. So attempt will return an either if there was a failure. So if there was a failure, we'd have to roll back to the full handshake protocol. If it didn't, then we can just stop and we're good. Like if we try to reason about how, for example, first phase is implemented, you can obviously, like, this is what we've seen before. We log some stuff, we fetch our key, so our private and public key. We create this encryption handshake message here with our public key and some timestamp, and we send that encryption handshake to that particular node that we try to connect to. So this is this round trip method I was showing you guys a moment ago from the communication abstraction from the type class. So we send that particular encryption handshake message to that remote with a given timeout. And now, if we get the response back, so here if we get the response back, if we actually got it, then we will store that remote public key that we have from that node that we tried to connect to. It's being stored in a key value store. So this is this part. So we store that key here for that given remote, and then we just log that information. Then the second phase is pretty straightforward. It's basically the same thing. It's just log ping, then you create a protocol handshake message, which you have to frame, because right now those messages are being encrypted. When that is being framed, you one more time send it with a round trip function. So round trip, the idea behind round trip is that you send the message and you expect a response back. If you don't get that response back, it's an error under the given timeout. And you log it, and finally you store that information that you, through the communication abstraction, that you connected to that remote peer, and the algorithm is done. So now, once we've seen that, so let's talk about transport layer. So as I said, the whole communication, the whole abstraction of communication, like right now this type class communication like stores two different things. It stores a little bit of abstraction behind the transport layer, and also a few things from Academia protocol. Those should be probably decoupled from each other, but this is how it is. But you can guys see that most of the time we were using this round trip method. There is an equivalent which is called com_send, which just sends a message, and we don't really care about the results. Like, it may still return an error for some reasons, but we don't provide any timeout. We don't care about the response. We're just sending it. Like, if you receive it, fine. If you didn't, too bad. But most of the time, we are using the round trip method, which sends a message and expects a message back from the other peer. Now, the way that this abstraction is being implemented is by, not as you could imagine, the TCP layer, but UDP. So here we have unicast network, which sort of implements that abstraction. You don't see it here, but it does. And it's underneath, it's using this little unicast com. And unicast com is responsible for, let me show you. So unicast com is responsible actually for delivering the, implementing the abstraction of sending messages over UDP. Now, this is a problem for a number of reasons. One of the reasons is that, as I said, we most of the time we send messages when we expect responses back. But with UDP, you don't have that. So you have to implement that on your own. And this is what we do. And this pollutes the abstraction that we have within code. So let me show you an example. Remember how we had that proto here. And Proto had a header, but it also had a return header. And now we might be wondering why that is. And the reason for that is, if I send a message over UDP, and somebody will send a message back over UDP, I have to know whether that message is actually a response for my question, from my request, or maybe this is something different. Because network is not reliable, right? Messages can come out of order, they may die somewhere over network, or maybe the node doesn't exist. So I have to somehow distinguish between the messages that are coming, whether this is actually a response that I'm having for the request that I did. And this is where, so that informations are being stored in the return header. So somebody who's sending a response has to fill that return header with some information. And you can see how that pollutes code. So just to show you an example, where we have that peer-to-peer Scala, when we have that connect method over here, we take two arguments, peer and timeout. And peer, the type of peer is peer node, right? This is the abstraction that reference to what it means to be a peer. However, if we look, so remember this, peer node, right? But if we look at the communication abstraction, it already uses something different. It's using something which is called protocol node. Peer node and protocol node are two different things. So what is the protocol node? Well, if we will actually look it up, protocol. There we go. If we actually look it up, we see that protocol node is extending peer node. So protocol node is peer node and has some other additional stuff. One of the things that it is no longer a pure structure. While peer node was just a case class, it was just a structure holding some information, your identification, your endpoint information, like your host and port, and that's it. Protocol node is a more like a object-oriented class which has some state, and that state is being modified. One of the things that are being modified is the sequence number. So the sequence number and timestamp are exactly being used. So if you send a message and you receive message back, then you sort of try to run equality, whether the sequence number is the same as the one that you sent, and whether the timestamp that you sent is exactly as the one that's being returned. So this pollutes the abstraction. Not to mention it basically breaks the Scala code, because like if you have a case class and peer node is a case class and you extend it, forget about like equal and hash code contract that you have within the JVM. So this is broken and has to be fixed. I forgot what I wanted to tell you guys. So yeah, that's this part, that part as well. Okay, yeah. So having that, now we can talk about what should we do about it. So the number of things that we would like to fix. First of all, we are thinking to switching to a different transport layer and actually be using just TCP. Because that sort of makes sense. Even though Academia paper explicitly talks about using UDP, we can, because we have this abstraction of communication and we can divide it into transport layer and Academia into two separate abstractions, we can provide implementation that will be using that just TCP. Or maybe we can provide an abstraction that will be using UDP to do node discovery, but will be using TCP when we actually want to send bigger chunks of blocks. Because one of the problems with UDP is that if you want to try to send something bigger that doesn't fit your packet, right, like a blog, then you have to send few of them, and then you have to create also some sequence, and that sequence has to be rebuilt on the server side, on the recipient side. So you basically at some point start to re-implement TCP. At some point you're just re-implementing already existing protocol. So that's what we try to avoid, and that's why we probably will start first with TCP. And what we will use for that will be gRPC. So we'll be using gRPC from Google. Each node will run as a server and a client. So whenever you try to connect to other node, you will use the other node service, and you will be a client, and the other way around if somebody tries to connect to you. Nice thing about gRPC is also that we have a TLS implemented there for free. So we are also thinking about completely removing from the connection, the connection protocol that you saw, really nice animation on the slides, had two-phase handshake. We are considering completely removing the first handshake, just having the second handshake. Because if you think about it, If each node will run its own OpenSSL server and will have its own public certificate, self-signed, it doesn't matter, that certificate generated by OpenSSL can become that node's public key, which can be part of its identification, so it will be part of its address. And now, if we will be using gRPC service, which will be using TLS, we can learn about each party's public certificate because that information was already exchanged, so we don't have to do it. And by default, every message that will be sent will by default be encrypted by TLS. So we have that for free. And we don't have to re-implement everything from the scratch. It sort of exists. It's been here for 25 years. It's pretty solid at this point. So that's one of the things that we'll be doing. Yeah, so by going to gRPC, we sort of deal with two things. We deal with that trying to re-implement TCP on UDP, and also we have a better encryption. Now, if you've seen Mike's presentation from yesterday, some of you guys might have been on his presentation. When he was writing a simple contract, he was showing you how you will have to right now, just in order to run REPL, you run Docker with like a REPL flag and runs for you. In upcoming version, which will be released pretty soon, I think next week, this is a little bit different. So now REPL becomes just a thin client that connects to the node. So you will run your node as a process here, and then you run in a separate window, a command line, a REPL. And that REPL will connect that node over the gRPC service. So that's a separate gRPC service that we have. This is not the one that will be used as an underlying transport layer. This is something we provide as an API for you guys to sort of communicate with Node. So it's not, at the moment, it's not going to be a REST API, it's going to be a gRPC API. There's probably going to be a REST API as well at some point if it's going to be needed. But the default one will be gRPC. So now the REPL, as it will come in the next version release at the end of April, beginning of May, will be a thin client that connects to your node. You type something in, some Rolang, it sends that Rolang over to the network, interpreter evaluates it, gives you a response back, and this is what you see. All right? That gRPC service will be growing with functionalities. So one of the things that you will most likely get in this release as well is ability to see from the API how many nodes actually are connected to your node. So you no longer have to just look for logs and all that. You will have ability to basically just say, hey, how many nodes are connected? Which nodes are connected? Who am I talking to? And yeah, once the node will grow with its functionalities, those functionalities will be reflected also on the gRPC API. And if you run node with --help, you will get all the list of all possible commands that you can run on it. So I think that's pretty useful information because I think it wasn't covered before. And yeah, so you will have the ability to also to specify where your node lives and stuff like that. And also one nice feature, and that I think wasn't covered on the Mike's and Kent's presentation as well yesterday as well yet, because that's a new feature, is that on version 0.2, the only thing that you could do was run, I think, just run REPL. But also you have one additional feature. I don't know if it's coming in this release. Maybe it was released on the previous release as well. But I think it's worth mentioning that there is a --eval flag, where what you provide is you provide a file to your Roland code. So you don't have to copy paste like Mike was doing the other day to your REPL. You can create your a little bit more complex Roland code in your file somewhere out there, and then just run it by calling docker rnode --eval and provide a path to that file. I think that's all I have on my side. I don't know if there are any questions at the moment. You could use the mic, please. Yeah.
Yeah, a couple of questions. Thanks, Pawel. Ed Eichholt from Pythia. Will the nodes boot up with a list of well-known nodes, and will those well-known other nodes be retrieved from the registry or another smart contract?
So I cannot talk about the future release requirement, what they're going to be, because I don't necessarily know at the moment. However, I can tell you how it is right now. Right now, there is a running Bootstrap node, which its address is well known, it's documented, it's available on the website. And the way you run it is you run your node, and there's a flag -b or -- bootstrap where you provide the address of that particular node, and then your node will connect to it. But eventually, oh no, sorry, yeah, I'm actually lying. Let's roll back. No, there is a list right now. It's not a list, it's a single node, as I remember it. It's hard-coded within code. And yeah, if you just run node, it will try to connect to it. But however, you can specify to which bootstrap you would like to connect by this flag. So you can run your own little network of RChain at home, right? You can instantiate a bootstrap here and then run a couple of computers. Maybe your fridge may run it if you have one with Java, and it will just create its own little network here. But right now, there's like a single node that is hard-coded.
Okay, so if node A and B connect to this well-known hard-coded, will A and B share each other's information?
Oh yeah, so that's how.
Yeah,
so there will be this node discovery. So that let's say there's a bootstrap over here, right? Over here, this is a bootstrap, and I connect to it, and you connect to it, and so when I connect to him, he has its internal list of nodes, and that will be me, and I have my little node of a list of nodes, and that little table, and that's him. But then you connect to him, and once you guys are connected, he will tell you, you know what? There's this little guy Pawel here. You should learn about him, and he will send you that information about myself, and then you will try to connect to me, and like we will connect, and I was like, I will tell you, you know what? There's this guy Bootstrap, and you'll be like, you know what? I know.
Got it.
And all three of us will have information about each other.
And is there version checking of some sort? Let's say one of the nodes is outdated from a version perspective.
So, okay. So the way that it's being implemented is being implemented using protobufs. So we're not sending any JSON information whatsoever. So if any, and all the fields are optional. What it means is that even if it is going to be a new version, it will still be able to run on the same network. It might just ignore some fields which are new. Might be not aware of some information that you're passing in, but that isn't really a problem.
Okay, so those version issues would have to be addressed above at a system layer,
on the business
blessed
layer.
contract, something like that.
So what for example, we experience right now is that with the release of 0.2, we had a running network of nodes somewhere out there, and with that Bootstrap being hard-coded within our code. And if you try right now with the current implementation, like I don't know how it is right now, but at least 2 weeks ago, if you tried to connect to that network, it completely failed. But the reason for that, why it failed, was that I've added the encryption last month, and the previous running node didn't run encryption. So now I'm sending him back an information, but that information is encrypted, and that node is like, the hell, right? But those are the breaking stuff which we will, we can still break those little things because we are under development. But once we reach the 1.0, obviously things like that will not happen. However, the underlying message that we might be sending might be growing, but it will never be deleted. It's like even sourcing kind of way of making communications work.
And then at what level will it be, at comms or above? Will things like node reputation or denial of service prevention happen? Is that the comms layer or above it?
Denial of service is comms layer, but the second question was?
Well, so let me drill on that one. So how will comms address denial of service? Will it blacklist another node, for example?
Oh, okay, so on the different layers, like in terms of like what on the blockchain and that information, whether somebody is lying and all that is a different layer.
No, I'm just saying like.
But if for example, so if you're being flooded, if your node is being flooded, you're screwed, I think. But the node, so the whole network isn't, because Kademlia can figure out and can just bypass you with the information. So the node discovery will still like some node will try to learn, as a node, try to learn about some other node that is somewhere there. The algorithm tries to go through you, but never passes you because you're constantly being ignored because of the denial of service attack. Then Kademlia will just bypass you. will just pick another node which responds. Because I send you a message, listen, do you know about this node? This is how the node discovery in Kademlia works. I send you a message, listen, I'm looking for this node. Can you send me a list of nodes who are probably close to him? Right? And then you give me that message back, and then I send that information to those nodes that you just listed. And this sort of like converges towards the final node that will tell you, that's me. But if I send you that message and you're being attacked, I don't get a message back, I'll just send the same question to somebody close to you. In Kademlia terms, what close means is that should be a different presentation. But anyway, I will just bypass you and reach that information. So this is how it's being dealt with on the comms layer.
So let me go ahead. Is that addressing the question about denial of service?
Yeah, well, obviously, going up the OSI model, going up the stack, you can block it wherever you're at, right? Physical layer, layer 2, layer 3, layer 4. So I would imagine node operators, and the question is, do we do that for them and already build it in and do different layering? Obviously, in the COM stack, it does that, in the contract stack, so each layer, but the sooner the better, right? Getting rid of garbage or malignant packets is better. So I think that will be built in. I kind of touch on it on the one I'm doing and stuff. That's where I've had a lot of background and stuff. So I'm kind of giving different tools and methods and stuff. I'll even walk through Suricata and Snort and using IP tables and like NQ to work with that stuff. We'll see how much time we have and stuff. Maybe we can get out and bust out some stuff.
So we do expect to do some denial of service blocking at the comms layer.
I would. Sooner the better.
Okay.
You know, so I'm assuming that, and obviously you'd have reputation on different layers of the stack. So.
Okay, so I was addressing a different issue. If that machinery will not work, you will not break the whole network. That's what.
Yeah, you can do it in Kademlia and stuff. That will take care of it too, right? It's just where do you want to start at? So it works great right now. Like you can't connect without encryption or without talking the right talk on the, if I send a UDP scan, obviously I'm not going to get anything back because it just drops it because it isn't talking the right language or hooked up with encryption. So it handles it in there, but we can do it whatever, or put that onus on the individual node operators and stuff like that. So if we want, whatever people want, so we'll probably cover it all. So
I think there was another question.
Yeah, so I want to ask right now, how tied to the transport are you in your design?
So as you saw, I am not tied. So I can actually show you the code. The one that I show you is that, I'm lying, but I'm not it's not that bad as it used to be. So let me show you. So this is the logic of connect. And connect requires some capabilities from the final type that you will be using it with. And one of the capabilities is communication. At that point, when I'm implementing, for example, first phase here, I don't really care how the communication is implemented. It's a type class. You have to provide me an instance of a type class. I don't care. So it is not coupled, but it is. So it's really hard to explain without going really, really deeply into the code. But because we are using UDP, I cannot, let me show you something. Communication. See, as you will see, what I'm sending is something which is called protocol message. But protocol message is not the class that is being generated by protobufs. It's not that from protobufs I'm having some classes that are being generated. It's not that little thing. And why is that? Well, the reason for it, let me just jump there. There we go. The reason for it is exactly this. I have to keep timestamp. I have to have header, and there's also our messages which are called responses, because response needs to have a return header. So this is where the underlying transport layer licks in, and this is what's pissing me off. Because I cannot really write a pure functional code at the moment because I have to deal with all that crap. And yeah, so this is where, so even though from from the business logic perspective, it seems almost like, hey, this is just an abstraction and somebody will implement that and the whole thing will work. Well, not really, because underneath there are some elements from the underlying implementation of that abstraction which are leaking into design. And this is one of those little things. And there are more. Not that many, but few. So what happened was when I joined project, COM was written sort of more imperatively, and we had no way of testing it. Right now we have tests where we can reason about how the communication will act upon different circumstances. And the way that was being done, we just put a boundary between the functional code and imperative code, and that boundary was slowly being pushed down. But there is some stuff which I call where the dragons live, Dungeons and Dragons, and that's where it leaks. So, and this is what we try to address. So one of the things that, for example, how Kademlia is right now implemented. So Kademlia is its own protocol, its own algorithm, but it needs to have ability to send messages. Right within the algorithm, there is like a concept of sending a message. So that concept is a little bit tightly coupled in the implementation. The way I would like to re-implement Kademlia at the moment is make it its own executable, its own jar, so you can even have data implementation and use it for something different. Write your own BitTorrent if you want. And that Kademlia will just be using abstraction of the transport layer. We will have like a type class called transport layer, but that will be completely abstract from the Kademlia perspective. It will not leak to the Kademlia implementation. You will be able to provide UDP, TCP, or TCP with UDP, whatever you want, but that will be the concern of that transport layer, not of the Kademlia protocol, as it is right now. Does it answer your question?
Yeah. Is it all right if I provide some reasoning for this?
Yeah.
I help run MetaMask. It's a browser extension, and it's an Ethereum wallet. And I'm interested in getting it to work with our chain. Right now, in order to serve all those users, all their blockchain data lookups, we have to run a bunch of hosted Ethereum nodes. I'd much prefer if it ran as a light client and communicated with the network normally.
Oh, so that's So, but for that you will have a separate API. You will write your code that you will just communicate with that API. It will be a gRP service which runs on the node, and you can connect to it with any language that you prefer. I mean, any language that gRPC creates its classes for. But majority of languages that we know and we use out there are sort of implemented.
So I'd actually like to avoid that. We're doing that now, and serving users with that is cost prohibitive. So it would be nice if they were first-class citizens. I mean, still light clients on the network. The problem is we don't have TCP UDP access inside of a web extension. So we'd like to connect over WebSockets or WebRTC or some other things. So anyways, that's why transport agnosticism is really valuable for me.
I see. So we can maybe cover that in detail. Maybe we can also take Nash for it, but because I don't know if I'm suitable to answer those kind of questions. Right? So when I joined the project, I was excited about the blockchain, and then Nash told me, well, you're going to be doing communication layer, which has little to do at the moment with blockchain. So I'm more focused on that. So if there are some more blockchain questions, then probably we should ask somebody else at the moment.
So it sounds like you have a requirement.
I'd like to talk to the peer-to-peer network as a first-class citizen from the browser.
So if you're on Discord, just DM me, and we'll talk about your use case. Okay. And we'll get it on the roadmap. So I understand, Ed, you had a question about denial of service. Yeah. So typically, denial of service has to be shut down at the router level. You have to identify the IP that is attacking your service, your server, and you have to shut it down there so those requests don't make it through the router to your box. This is something pretty common that sysadmins, I'm looking at you, Jeremy, know how to do this. And whatever we get basically for free from TLS or SSL or our comms layer implementation, that's what we'll get for denial of service. But we're really going to count on sysadmins to, if they've got a node that's being DOSed, they're going to have to go and shut that down at the router at the IP address, right? We're not going to support it too much in the software level.
The denial of service at higher levels, right?
Yeah, the bigger, if you have more bandwidth, this is the same thing like Cloudflare and stuff like that work with. If you have more bandwidth, you can crush anybody, right? I can shove unlimited packets down. Unless it's stocked in one of the upstream routers, it's just going to keep coming down.
Well, actually, so he's talking about software, so everything's going to cost.
Yeah.
So if you want to send a whole bunch of transactions to the Archain network, you're going to spend a lot of money doing that to try to DOS out a server or a shard.
They're going to pay for it.
They're going to pay for it, and those are transactions on the Archain network. So is that a bad thing? I don't know.
Hey, I appreciate you addressing this. I'm talking about like denial of service at the comms layer. So above the router, and in essence, below the cost layer. So let's say I throw, hundreds of thousands of connection requests with valid protocol connections and attempt a buffer overrun of the peer node list or something like that.
So that's usually what happens before the system administrators identify a DDoS, right? A directed denial of service attack. So we'll have monitoring in place. They'll know they're getting hit pretty hard, right? The server server metrics will indicate that. So that's what we're going to do to support them in identifying that a DOS attack has actually happened. So they'll be able to look at their metrics in Prometheus and identify that there's a whole bunch of connections coming in on a particular server, and they'll identify that server is being DOS, and they can then go ahead into their router and blacklist that IP address and make sure those connections don't come through. So that's how we're going to address it, right? So we're providing all the monitoring tools for sysadmins so they can make sure that everything is running smoothly on the network.
Yeah, that's where something like pfSense and intrusion prevention enabled on it. Like I said, Suricata is probably the best right now. Everyone's probably familiar with Snort and stuff like that from back that didn't use security, but Suricata, and you can do that inline. And like I said, we'll cover that, and continuing, we'll add support and like best practices and stuff for that for any of the node operators or people that want it, because it is important, right?
You good?
All right. Are there any more questions? I guess not. So thank you very much, guys.